Example 5. Determine the horizontal and vertical components of reaction on the member at pin A and the normal reaction at the roller B in the figure. The first thing that we are going to do is we are going to draw our free body diagram. And if you can observe, incline at B is 30 degrees. Okay, we draw our free body diagram. Let me zoom in a little. Oh, zoom. Okay, so we have 0.3 meters. So we have this is A and this is B. Okay, 0.3 meters from A, we have a force of 750 Newton going down. So let us label this 0.3 M. And from here to here is also 0.3 M. Okay. Now from the perpendicular distance from A to B is 0.2 meters. From here to here is 0.2 meters. Okay, so at A, we have our going up A sub Y. Now, for our B, if you can observe, whenever there is a force, like say, any structure on an inclined, especially that this is a ruler, normal yun ng ato ang force, right? Normal to the point of contact or at the surface, right? So, and since this is 30 degrees from our horizontal, it means that this here is also 30 degrees, because if we try to get our another horizontal line here, this is 30, this is 60, so this is another 30 degrees. So therefore, if we are going to redraw that here at in our free body diagram, this is our normal force B, say NB, or we just call it B, oh yeah, NB, and then we have this is 30 degrees, so we have going up and B sub B Y, and to the left is N sub B sub X. So if we can observe from our free body diagram that only N sub B has a horizontal component and it is going to the left. So therefore, to counteract that, in order for our structure to be in equilibrium, so we have A sub X to the left. Okay, so if we do forces, a summation of forces either X or Y, we will end up with two unknowns, right? And that is A sub X and B sub X for summation of forces X, and A sub Y and B sub Y for summation of forces in the Y direction. So the first thing that we're going to do is we use the third equilibrium equation for our set 1, and that is we do moment about A. Summation of moment about A is equal to 0, assuming counterclockwise positive. Now, NBY follows, the Y component of our normal force N sub B follows a counterclockwise moment, while our X component follows a clockwise moment, as well as our 750. So this becomes now NB sub Y, and its perpendicular distance, that is 0.3 plus 0.3, so that's 0.6 times 0.6. minus NB sub x times the perpendicular distance from A to B is 0.2 times 0.2 minus 750 times 0.3 is equal to 0. Now, NB sub y and NB sub x can be expressed in terms of the unknown N sub B because it is the angle is provided. So NB sub y that is equivalent to if knowing that our 30-degree angle is measured from the vertical, right? So NB sub y becomes N sub B cosine 30 degrees times 0.6 minus NB, and our x component becomes sine. So that's NB sine 30 degrees times 0.2 minus 750 times 0.3 is equal to 0. Now, if you can observe, there is a common factor in our equation, and that is n sub b. So we will do it simultaneously. We transfer 750 times 0.3 to the right-hand side of the equation, and then we factor out n sub b. So this becomes n sub b quantity 0.6 cosine 30 degrees minus 0.2 sine 30 degrees is equal to 750 times 0.3. Okay, and then we divide both sides by the value in our parenthesis so that we can find n sub b, and this should give us n sub b is equal to, I will do the new denominator first because it's quite long. That is 0.6 cosine 30 degrees minus 0.2 sine 30 degrees, and then our numerator is 750 times 0.3. So if we do the solve this expression, and sub b is equal to we have 0.6 times cosine 30 is 0.519615242 minus parenthesis 0.2 sine 30 is 0.419615242, and then our numerator is 7 parenthesis 750 times 0.3 close parenthesis divided by answer should give us 536.2054981 Newton. So this is our normal force at B. So now if you can observe, we actually you can either do the moment at B or at A, you can choose. However, we deliberately do the moment about point A because if we express our normal force N sub B in terms of its components X and Y, we can solve it, we can express the X and Y component of our NB in terms of the single force NB, simply because the angle is provided 30 degrees. Now, if we did the moment at B and we do a moment summation, we will end up with two unknowns, and that is A sub X and A sub Y. Because again, the angle that our resultant A, okay, is not given, right? So we will end up with two unknowns. So we included in our analysis that it is better to do the moment at A. So since we have calculated our NB now, we can now solve for our a sub x and a sub y by doing force summation. So summation of forces F sub x is equal to 0, assuming to the right positive, then this becomes A sub x minus NB sub x is equal to 0, and A sub x is equal to NB, and NB is sine, x component is NB sine 30 degrees, sine 30. And NB is 536, so that's we substitute the value that is 536.205489. 4981 then. 4981 times sine 30. So our A sub x is equal to answer times sine 30 is equal to 268.102741 Newton. That is our value for A sub x. Now, let us proceed to doing some force summation in the y is equal to 0, assuming upward positive. So this should give us A sub y plus B sub y minus 750 is equal to 0. A sub y is equal to positive 750 minus, this should be NB sub y, sorry. Let me put N here. Okay, minus NB sub y, and this is equal to 750 times N sub B cosine 30 degrees, right? So we substitute our value for NB. Let's negative 750 minus parentheses. That is 536.2054981 cosine 30 degrees. So our value for A sub y is equal to 536.2054981 times cosine 30, 750 minus answer is 288.632417 Newton. So there you go. That is our value for A sub y, A sub x, and the normal force, a normal reaction at the roller B, which is provided here in our figure.